Hey everyone, and welcome. Ever wonder how Netflix just knows what movie you want to watch next? Or how a machine can learn to predict trends? Well, you're in exactly the right spot. Today, we're going to dive into the beautiful and powerful world of linear algebra. And trust me, it's the secret language that powers pretty much all of modern data science. So let's kick things off with the big question, right? The one that's at the heart of machine learning. How on earth does a machine, a bunch of code, actually learn to spot a pattern in this massive ocean of data? How does it find that one perfect line through a messy cloud of points? Well, I'll tell you this much. It is not magic. The secret sauce, really, is that it all starts by describing that data with a super powerful and precise mathematical language. You know all those buzzwords you hear: principal component analysis, recommender systems, linear regression? Well, guess what? They're all built on the exact same foundation, the same grammar. And that grammar is linear algebra. It's what gives us the tools to talk about data, to change it, and most importantly, to find the hidden secrets inside it. Okay, section 1, the world of vectors. We're going to define the environment for our data. So, first things first. Before we can do anything cool with our data, we have to define the world it actually lives in. I want you to think of our data points as vectors. And just like we have rules in our world, physics, these vectors have rules for their environment too. And that special environment, we call it a vector space. So what is a vector space? Don't let the name scare you. It's really just a collection of vectors where two key things are guaranteed to work every single time. 1, you can add any two vectors together, and 2, you can multiply any vector by a number. We call that a scalar. It just scales it up or down. As long as these two operations follow a few simple, consistent rules, boom, you've got yourself a valid space to work in. And this is a great way to visualize it. This is the parallelogram rule, and it makes adding vectors super intuitive. If you want to add vector A to vector B, you make a parallelogram. The answer, A plus B, is just the diagonal. And here's the key part. The result is guaranteed to be another vector living in that same space. This super important rule is called closure. It basically means you can't accidentally leave the universe you're working in. It keeps everything predictable. Okay, so this brings up a really cool idea. Let's say we have this big valid vector space, right? Like all of 3D space. Is it possible to find smaller, little self-contained worlds living inside it? Like a whole other valid space just tucked away inside the bigger one? Can that even happen? Well, the answer is a big yes, and we call these things subspaces. But for a collection of vectors to be a true subspace, it has to pass a little 3-part test. It's like a VIP checklist. Number 1, it's got to contain the 0 vector, the origin. Number 2, it has to be closed under addition, meaning if you add 2 vectors from the club, the result has to stay in the club. And number 3, it's got to be closed under multiplication. You scale a vector, it's got to stay in the club too. And this image just makes it crystal clear. See that blue plane? It slices right through the origin. That's a perfect example of a valid subspace in 3D. Any 2 vectors you pick on that plane, you add them up, and guess what? The result is still on the plane. But now, look at the red plane. See how it's kind of floating? It completely misses the origin. It fails that very first, most important rule. So, it's not a real subspace. The big takeaway here? A subspace must go through the origin. No exceptions. All right, next section. Matrices as transformations, the actors that change our data. Okay, so we've set the stage, right? We've got the environment for our data. Now let's bring in the main characters, and those are matrices. Now, it's super easy to just look at a matrix and see a grid of numbers, but that's not where the magic is. Their real power is in what they do. A matrix is an action hero. It's an operator. It's a machine that transforms vectors, moving them from one place to another. They are literally the engines of change for our data. So to really get what a matrix is doing, we've got to look at its anatomy. It's like every single matrix out there, doesn't matter how big or small, is defined by these 4 crucial parts, these 4 fundamental subspaces. You've got the column space and the left null space over in the output world, and then you've got the row space and the null space in the input world. And these 4 things together, they tell you absolutely everything about what that matrix is going to do. And this diagram right here, this is what some people call the big picture. It shows exactly how a matrix, let's call it A, acts like a map. It grabs a vector from its input space and zaps it somewhere else. More specifically, it takes anything from its row space and maps it perfectly over to its column space. So what about the null space? Well, that's where things get interesting. Anything from the null space gets completely squashed, just flattened down to the zero vector in the output. It's like a black hole for vectors. And these four spaces, seriously, they explain everything a matrix is capable of. All right, section 3, decomposing complexity, or looking under the hood. Now, let's be honest, some matrices can look super complex and intimidating. But just like a good mechanic doesn't get scared by a complicated engine, we can pop the hood on a matrix and decompose it, break it down into its most important parts. And when we do that, we get to see what it's really all about.
So here's a thought experiment for you. When a matrix gets to work on a space, stretching it, twisting it, rotating it all over the place, are there any special vectors? Any vectors that are kind of stubborn, that just refuse to change their direction? They might get stretched or maybe shrunk, but they stay pointing along their original line. Do vectors like that even exist?
You bet they do, and they are so important. We call them eigenvectors. Just look at this. The normal vector x gets totally knocked off its path. It gets rotated and stretched into ax. But look at our special vector v. It doesn't budge from its line. It just gets stretched by a factor of 2, becoming av. That v is our eigenvector. And that scaling number, the 2, that's its eigenvalue. Think of these eigenvectors as the stable axes, like the very skeleton of the whole transformation. Now, eigenvectors and eigenvalues are awesome, for sure. But there's a catch. They mostly work for square matrices. But what about all those non-square, rectangular matrices? Those are everywhere in data science, right? Where you have way more data points than you have features. So how do we find the deep, fundamental parts of any old transformation? For that, we need a universal tool. And that tool has a name, the Singular Value Decomposition, or SVD for short. Now you might see a formula like A equals U sigma V transpose and kind of panic. Don't. Geometrically, it's actually beautiful and super simple. It's just a 3-step dance. Any transformation, any of them, can be broken down into this. Step 1, you rotate. Step 2, you stretch things out along the new axes. And step 3, you rotate again. That's literally it. Rotate, stretch, rotate. And this visual just nails it. We start with a nice simple square grid. The first part, that V transpose, does the first rotation. Then the middle part, sigma, does the stretching, turning our square into a rectangle. And finally, U does one last rotation on that new shape. But here's the real aha moment. That stretching part, that's where the gold is. It isolates what's most important in the data. The biggest stretches point to the biggest, most significant patterns. And that's why SVD is such a powerhouse for things like dimensionality reduction. All right, section 4, solving real-world problems with the least squares solution. Okay, so we've got the rules of our universe, and we've got the tools to take things apart. Now, let's put it all together and solve one of the most common, most practical problems in all of data science. So here's the scenario. Picture this. You're trying to fit a single line to a whole bunch of messy, noisy data points. This sets you up with a system of equations. Ax equals b, but the problem is it's overdetermined, which is just a fancy way of saying you have way more equations or data points than you have variables to solve for. And because of all that noise, your target, that vector b, isn't actually sitting in the nice flat plane of all the possible perfect answers, which means technically there's no perfect solution. So, what now? If a perfect answer doesn't exist, do we just pack up and go home? No way! We just change the question. The new goal isn't to find the perfect answer, it's to find the closest possible answer. So how do we find that one specific point on our plane of possibilities that's as close as it can possibly get to our real target? And the solution is just, well, it's geometrically beautiful. We find that closest point by just projecting our target vector b straight down onto the column space. Think of it like casting a shadow at a perfect 90-degree angle. This is called an orthogonal projection. The spot where that shadow lands, that's our point P, and that is our absolute best guess. The little gap between our guess and the real thing, that arrow vector E, is now as short as it can possibly be. And this right here, this is the core idea behind almost all of linear regression. So let's just quickly recap the path we've traveled. We started with vector spaces, the rules of the game. Then we brought in matrices, the players that make things happen. We looked under the hood with SVD, our universal toolkit, and then we used all of that to solve a real-world problem with least squares. See how it all connects? It's this beautiful, logical path from abstract ideas right down to a practical solution. Okay, before we wrap up, I want to give you a few common pitfalls to watch out for on your own journey. First, super common mistake. A matrix is a tool, an operator. It's not a space. It's the columns of the matrix that define a subspace. Second, please, I'm begging you, always check your matrix dimensions before you multiply. It'll save you so much headache. Third, independent doesn't automatically mean orthogonal. They're not always at 90-degree angles. And last but not least, get comfortable with things not being perfect. Real data is messy, so finding the best possible answer is the real win.
And that brings us right back to where we started. Why does any of this matter? Because this stuff isn't just theory locked away in a textbook. Remember those eigenvectors? They are the absolute engine behind principal component analysis, which finds the most important directions in your data. That SVD we broke down? That's the heart and soul of recommender systems, finding those hidden connections between what you like and what other people like. And least squares? It's the hardworking engine of linear regression. At the end of the day, linear algebra is the language we use to find the hidden insights in data. It truly is the language of data science.